Hello, thank you. Yeah, hello everyone. So I am Harsh Gupta. I'm a software engineer in Money Forward, and my topic for discussion for today is escape analysis in Go, understanding and optimizing memory allocations. So before going into the topic, a brief disclaimer that I'm not good with Japanese. So the text you'll see on the slides, the Japanese text is being translated by Google Translate. So if there are any inconsistencies, I apologize for that. Okay, so let's start. So before going into the main topic, let's discuss about allocations first. So a program has two places to allocate the memory, stack and a heap. Stack is for the allocations which a function uses for allocating its local variables, and heap is kind of a memory which is whole program's memory where allocations like global variables happen. So the case with Go is exactly the same. We have a stack and a heap, but point to note is that in Go we have multiple Go routines. So each of the Go routine will have its own stack, and it's the same essentially. Also, one more thing to notice is that uh, stacks allocations are preferred generally, but what is the reason? So the reason number one is allocations are faster on the stack. They are faster, although, but the benefit isn't that great because our programs usually runs on microsecond or millisecond range, and allocations differ only in nanoseconds range. So it's not much of a gain, but still it is if you are doing a lot of allocations. The reason number two is that stack allocated variables are automatically deallocated whenever the function returns, so you don't need to care about that manually. You just don't worry about the allocations that you do on stack. But on the other hand, the case is different for heap. Whenever you do any allocation on heap, it requires manual deallocation. If you remember, when we wrote programs in C, there was malloc and free. We have to do use malloc to allocate, and then we have to free that memory by ourselves. Or if you don't want to do manual deallocation, you can use a language which has garbage collector, which does the job for you. Garbage collector is good, but it causes latency, and the latency it causes is not for the part of the program that does the allocations, it for the whole program. So it kinds of slow down the whole program. It doesn't care about the part which is doing the allocations. So this is the reason number two. The next reason is about the fragmentation. If you remember that the heap allocations kind of sometimes leaves gaps in the memories, and that's called fragmentation. But that doesn't happen with the stack. So it is kind of a way of utilizing the memory very efficiently. So these are particularly the reasons that we prefer doing allocation on stack and not the heap. So yeah, so that's how I proved my point that stack allocations are better. Now look at some examples. So let's start with a simple example without involving any pointers. This is yeah, there is one function next int which takes an integer as an argument and increments it and returns it to the main function. So this integer I here is allocated on the stack of this function next int, and then there we just increment it and then return the value to a1, to this variable, which is also living on this main function stack. And if you run this, no crazy yeah output, the one that we want. So this is how it works. So yes, so this variable 10 was in the main stack, and then we passed it down to the next int, and it created another variable I with the same value. So no pointers involved here. Now let's take another example where we have pointers. So in this case, the function is almost the same, but in this case, the function is next int with ptr with pointers. So it takes not the integer, but its address, the pointer, and after yeah, it takes the pointer, it increments the value and returns the integer, not the pointer. So in this case, this variable a was living on main function stack, and then we pass the pointer, the address, which was referencing this, or which was on the main stack. So the address is coming from main function stack, and then we increment the value and return it. So in this case, when we come here at this line, the point to note is this variable a and its address is still valid, because the main function scope is still is longer than this function next end with ptr. So even if it finishes, it is still available. The main stack is always there. Whenever as long as it's there, you can always dereference their address and do any changes to the value. This as well works. Now let's move on to another example. In this case, we will return the pointer, not the integer. So this function is very simple. Just we create an integer on the stack, function stack, and then return its address to the main function. Now, this is a little tricky to explain. So this I was declared on the stack of get1, this function. And then when you return the address to the main, at this point, this function stack is invalid. You cannot access this function stack, but you have a pointer from that stack. So it should not work in theory, but if you run it, it works. And not just once, it will run every time. Trust me, it works every time. You might have also used this in Go with no problem, so it works. But how? That address is kind of invalid. It's dead, but still we are referencing it and we are able to do our work. So to explain how does that happen, let's take a same example, but in C now. So this is a C code of the same code that I just showed. In this case also, we have an integer allocated on the stack, and we return the pointer to that integer. And then here we dereference it and print the value. Here also, in this case, we assume that the value that we print should be 1. But when you compile this program, the compiler will throw a warning. And the warning will be that you are referencing a stack allocated variable when its scope is ended. So it will still compile and you can still run it, and it will sometimes even give you a value 1, which has a particular reason why it happens. But in most of the cases, it will just print a garbage value. So it is not very consistent. It's not very safe to do this kind of programs in C. That's why we had to keep a good care of our pointers in C. So what is happening here? So the thing is, in Go, that the example that I showed previously in Go, the compiler does an optimization in the compilation process, which is called escape analysis, due to which that example ran perfectly. But the same code in C will throw garbage outputs most of the time, because there is no concept of escape analysis built in the program. So that's one reason. And what escape analysis is essentially is, it's a technique used by compiler to determine whether a variable's lifetime extends beyond where it has been allocated. Like it checks whether the variable which has been defined in a particular scope outlives the scope or not. So it helps the compiler to decide whether to allocate the variable on the stack or the heap based on the usage of that variable in the program. So it happens, everything happens in the compile time. So it just does some smart work beforehand to check whether it's useful to allocate the variable on the stack on the heap. The goal of this algorithm or optimization is to minimize heap allocation as much as possible, because we know heap allocations are not good. So it will try, but if in certain cases it cannot do that, then in those cases it has to do heap allocations. And by minimizing the heap allocations, we are improving our program's performance indirectly and reducing memory usage, which has a lot of impact on our GC, which helps our GC a lot. So it has much less work to do. Next, let's discuss how escape analysis works in Go. So what the algorithm does, it ensures two invariants. One is that pointers to stack objects cannot be stored on the heap. It is reasonable because stack objects don't have longer lifetime than heap. So if pointers to stack objects if pointers to stack objects can be stored on the heap, then the heap variable can kind of dereference that value, which is invalid. So this is one invariant. The other one is that pointers to stack object cannot outlive that object. Yeah, same thing, but means different in different wordings. So how does it work? Next, it creates a directed weighted graph where the vertices are these variables and edges are the assignments. So in this case, for example, this will be P and Q will be the vertices, and P to Q there will be an edge, and the weight of that edge will be the representing the addressing or reference count. So in this case, it's an addressing. So for addressing, we do -1, and for every dereferencing, we just increase that number. So this, for example, in this case, there is an edge from P to Q with -1. What that means is like P variable is holding the address of Q. Kind of like Q has been captured by a variable P, and wherever P lives, it cannot outlive Q. So if P is living on the heap and Q is on the stack, then it won't work. So you have to do that Q's allocation on heap. So what it means is Q is going to escape to the heap. So that's how it recognizes. So similarly, like it iteratively walks through the whole graph and checks for the assignments that violate those invariants, and based on those, it marks some of the variables which require heap allocations in the compile time. So yeah. Also, the compiler, if it cannot definitely prove that the variable will not escape, it will live on the stack, it assumes that it will escape. So the thing is, if it is not completely sure, then it will always allocate on the heap. So there are some crazy optimizations in the algorithm which have been done, but if it's not sure, it will always allocate to the heap. So our job as a programmer is to make sure that writing a code through which compiler can understand easily where it's going to go, so it can deduce that it should be whether allocated on stack or not. In addition to the algorithm, there are some additional rules as well, where we have to like not just rely on the algorithm, but we have to check other cases. So some of the cases are like this. So the first one being variables with large size. So I tried creating some sample examples. So in this case, I allocated a slice of 64 KB, which was perfectly allocated on stack, sorry. And the other one, I just increased size with 1 and it went to the heap. It says it's too large for the stack. So it depends on machine. For my machine, it was this value 64 KB, but essentially there is a threshold after which you cannot you cannot actually allocate on the stack. You have to, it will definitely go to the heap. Other case, non-constant capacity sizes. So if you declare a slice, if it's constant, it will live on the stack. Otherwise, if you declare a variable size, it will escape to the heap. So we need to be careful here. If we know the size of the slice we are initializing, it's better to declare it with constants. Next one is the case with closures. So for closures, if you pass the value as arguments, it does not escape. But if we just capture if the closure captures the variable directly, it will escape to the heap. So that's one more point to take care. let's do the final example now. Trust me, it's the last one. So you might have sometime used IO readers interface. IO buffer implements that reader interface, and the function read function looks like this. There is an argument of the byte slice that you have to provide, and then it returns the integer of bytes it read or an error if there is any. So what initially I thought is, why this function looks like this, why not like this? So I created my custom reader where I just call the read function and it will return the byte slice. I don't have to create a byte slice beforehand. It will just return the number of bytes in the byte slice that it reads. So I tried creating an example. This is the code. So created a constant size slice, just for example, and then I created two functions, read1 and read2. One uses the io.buffer bytes, and the other one uses my. So here I pass the argument of a byte slice, and here I don't. And then I check the compiler. So one important point to note is we can check what's happening, what optimization the compiler is doing by this running this command. So in this, the M flag is to to tell the compiler that you want to print optimizations it's doing, and this L is for disabling inlining. Inlining sometimes hinders, so it's better to disable that. So what it prints is that this slice escapes to heap on line 12. So this one, sorry, yeah, this one is going to escape, and then B does not escape. So this one does not escape. So what I am doing is what I created, the function I created is going to escape the slice. I'm declaring here in this function. So it's not good. So there is another reporting method. You can just increase the number of verbosity. You can use 1 to 4 values here to make your optimization print the logs more verbose. So for this into you can see more details. Yeah, but yeah, there weren't fitting in my slide, so I just cropped them. Then I ran benchmarks using the same two functions, read1 and read2, and then the results are here. So for first one, the io.buffer package, it's 2 nanoseconds per operation with no allocations, and for my it's almost 5 times slower, and I also have one allocation. Then the time it ran, I also visualized the results with pprof. Pprof is a great tool to visualize about memory and CPU usage. So it says I allocated almost 3.3 GB of memory. I essentially I wasn't using that much memory. Garbage collector was handling this much of memory, which is bad. So that's what was happening. So yeah, that's the point. It's always better to pass as arguments rather than returning the variable. So these are some few summary points. So first point is, like, we should optimize for correctness first always, and then if we know that our program is not working fine, then we should look into all this, and then check for optimizations in memory, in performance. Next one, from the examples that we have discussed, we know that sharing pointers down usually stays on the stack because the function that is passing the value is going to stay longer than the function which is using that value. Next thing, sharing pointers up usually escapes to the heap because you are returning the address of a variable which was on the stack. So that has to be allocated on the heap. So that's one suggestion, that we should try passing variables as arguments instead of returning them. And yeah, next is about the closures that I just explained, and also the size. So these are the points that we discussed. So I think we are running out of time. So yeah, that was all. There are some FAQs. I'll actually post the slides on my GitHub. You can take a look. Well, so yeah, that's was all from my side. Sorry, I took much time, so we couldn't discuss more. Yeah, thank you.